At 9:20 on a cold February morning, daylight exploded into fire over Chelyabinsk. There was no warning. A sudden flash brighter than the sun, and windows shattered for miles. This was not the planet killer everyone fears. It was a small 20-meter asteroid we never saw coming. Why do these unseen, much smaller objects pose the real and overlooked risk? The answer upends everything we assume about asteroid threats. When the asteroid entered the atmosphere above Chelyabinsk, it was traveling nearly 18 kilometers per second. At about 30 kilometers altitude, the object broke apart with a force estimated between 400 and 500 kilotons of TNT, roughly 30 times the energy of the Hiroshima bomb. The explosion released a flash that outshone the sun, leaving many momentarily blinded. For over a minute, the city remained silent. Then the shockwave struck, shattering windows in more than 7,000 buildings and sending glass flying through classrooms, offices, and homes. More than 1,500 people were injured, most by shards of glass. Hospitals treated lacerations, eye injuries, and a few spinal fractures from falls. In the freezing February air, residents scrambled to cover broken windows with plastic and blankets. The freezing conditions made response and recovery more difficult. Dr. Peter Brown's analysis confirmed the energy yield and the scale of damage, underscoring how a 20-meter asteroid, smaller than many city buses, can disrupt the lives of an entire region without ever touching the ground. On the same morning that Chelyabinsk's windows shattered, astronomers were tracking a different asteroid making a close pass by Earth. This object, known as Duende, measured about 30 meters across, slightly larger than the one that exploded over Russia. Months before its approach, observatories spotted Duende and calculated its path. The Minor Planet Center issued updates as it drew nearer, confirming it would pass just 27,000 kilometers from the surface. That is closer than many satellites in geostationary orbit. News outlets covered the flyby in real time, and scientists watched as Duende slipped safely past. Despite the success, Duende and the Chelyabinsk asteroid were not related. One was predicted and tracked with precision. The other arrived without warning. Both events unfolded within hours of each other, yet only one was seen coming. This contrast reveals a gap in our ability to detect the objects that matter most. Most asteroids are difficult to see, not because telescopes are inadequate, but because of where they approach from. The detection process relies on spotting a faint, moving point of light against the background stars. This only works when the asteroid is far enough from the sun in the sky, what astronomers call a large solar elongation angle. Telescopes avoid looking near the sun's glare, so any object approaching from that direction is hidden. Ground-based surveys like Pan-STARRS and Catalina typically ignore the region within about 40 degrees of the sun. For nearly half the sky, sunlight overwhelms their sensors, making detection impossible. Even when conditions are right, these objects are often dark, reflecting less than 15% of the sunlight that strikes them, about as much as charcoal. Dr. Paul Chodas of NASA's Center for Near-Earth Object Studies notes that this is not a failure of technology or effort, but a fundamental limitation of geometry. If an asteroid's path brings it toward Earth from the direction of the sun, it can remain invisible until it is much too late. NASA's Center for Near-Earth Object Studies tracks every known meteor impact of at least 1 meter since 1988. In that time, more than 1,200 such objects have entered Earth's atmosphere. Fewer than 10 were spotted before they arrived, and none with more than a day's warning. These are not rare, once-in-a-lifetime events. Meter-scale impacts happen almost every month somewhere on the planet, often over oceans or remote land, but sometimes over cities. Month by month, these events quietly occur. The Chelyabinsk asteroid was about 20 meters wide, yet it caused thousands of injuries. Chelyabinsk reminds us how much damage a relatively small object can do. A 50-meter object, like the one that formed Arizona's Barringer crater, would release energy similar to a large nuclear detonation. 50 meters can be city-destroying under the right conditions. A 1-kilometer asteroid could devastate an entire country. 1 kilometer is not an extinction-level event, but its consequences would be catastrophic for a nation. For every giant extinction-level asteroid, there are thousands more in the 20 to 1,000 meter range, large enough to destroy a city, small enough to slip through our detection net. Thousands of these objects are the ones we actually need to watch. The real risk is not just their size, but how easily they can go unseen until it is too late. Years of careful tracking are needed to predict an asteroid's path with any real certainty. Even then, the math grows chaotic, as small gravitational nudges from planets slowly distort orbits, making long-term forecasts unreliable. When a new object appears with only days or hours before a possible impact, fast technical fixes fall short. Blowing up an asteroid risks turning a single thread into a cloud of unpredictable fragments. Attaching rockets or thrusters sounds promising, but most asteroids spin rapidly and are covered in loose, dusty material that defeats any attempt to anchor. The reality is that most proposed quick solutions collapse under the messy details of real asteroids and the physics that govern them. In 2022, NASA's DART mission proved that changing an asteroid's course is possible. The spacecraft struck Dimorphos, shortening its orbit by 32 minutes. But as DART's lead scientist explained, success depends on years of warning. With only days or weeks, evacuation becomes the only real option. Most impacts arrive with no warning. As detection gaps persist, our certainty is limited by what we can't yet see. The next surprise is already out there, unseen, but inevitable.